Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss drift velocity, conductivity and mobility in case of semiconductors. Let's begin. Let me consider a semiconductor. Having length small l. In that of semiconductor, that are free electrons as well as holes. Due to thermal inertia, the free electrons and holes inside a semiconductor are in a state of random motion, and these free electrons as well as holes move with all possible velocities in all possible directions, and the average velocity of these charge carriers due to that of thermal inertia will be 0. Let me take U1, U2 up to UN are the velocities of first, second up to nth free electrons inside that of semiconductor. Due to thermal inertia, that is its average energies as U1 plus U2 up to UN divided by n is equal to 0. Inside that of semiconductor, all the free electrons as well as holes move in random directions with all possible velocities, and the average energy will be 0. If an external electric field let that external electric field E with that of potential V is applied, therefore holes drift along that direction of electric field and the free electrons along the opposite direction of that of electric field. Here the positive potential, the negative potential, so electrons are moved towards that of positive potential. Similarly, holes towards that of negative potential. Therefore, the force acted on each free electron, the force acting on each free electron that is F is equal to charge of free electron into applied electric field, whereas minus E the charge of a free electron and E is the applied external electric field. Here let V the potential difference between the two ends of that of semiconductor. Potential difference between two ends of the semiconductor and small l, that is the length of that of given semiconductor. Therefore, the relation between applied electric field and the potential as electric field is equal to minus V by L. That one as equation number 1, this one as equation number 2. Let me put the value of E in that of equation number 1. Putting equation number 2 in equation number 1. So, F we obtain as E V divided by L, that is the force acting on each free electron inside that of semiconductor. Equation number here is let equation number 1, that is equation number 2, equation number 3, that one is equation number 4. That will be the force, then the acceleration, then acceleration with which the free electrons drifts along the opposite direction of applied electric field. So, that acceleration A is equal to force divided by mass of an electron, small m, mass of a free electron. Or here we put the value of F Therefore, A is equal to E V divided by M L, as F is equal to EV by ml. That is equation number 5. Now the electrons are moved like this way. Due to that of application of external electric field, and during that of motion of the free electrons, they collide with each other, and between two consecutive collisions they move in a straight line, and there will be a time difference. Okay. During drift motion, of free electrons, they collide with each other, and between the two consecutive collisions they move in straight line. Therefore, as they have the initial velocity, then the velocity changed. Let me take the change velocity. Let V1, V2 up to Vn are velocities of first, second up to nth free electrons inside the semiconductor. After the application of external electric field, electric field, and if you take the time intervals between a two consecutive collisions, as let T1, T2 up to Tn are time intervals between two successive collisions between two consecutive collisions of first, second, nth free electron. The collision of first electron as the time difference T1, next second one as time difference T2, like this. Therefore, these velocities v1 as initial velocity u1 plus a t1 time difference between that of collision, again v2 as u2 plus a t2. We continued up to vn as un plus a tn, and the average velocity with which the charge carriers drifts inside the semiconductor after that of application of external electric field is known as the drift velocity. The definition of drift velocity: the average velocity with which the charge carriers drift inside a semiconductor after the application of electric field is known as drift velocity. Okay. So, the drift velocity here in case of free electrons, therefore, drift velocity of free electrons is given by V of E as the average velocity v1, v2 up to vn divided by n. Put the value of v1, u1 at1, v2 u2 a2 at2 like this. u1 at1 plus u2 at2 up to un atn divided by n, separating as u1 u2 up to un divided by n plus at1 at2 dot atn divided by n. That result as 0, as we say in equation number 1. Initially the average velocity is 0 due to that of thermal energy, that velocity due to that of thermal energy, plus we take a as common, t1 t2 up to tn whole divided by n, or VE is equal to a T1, T2 up to Tn divided by n. That be the average time. Here we write a tau. Tau is for average time, which is known as the relaxation time, where tau, the relaxation time, which is equal to T1, T2 up to Tn divided by n. Equation number 6. The drift velocity of free electrons. If we put the value of acceleration or VE, value of acceleration EV by ml, that expression is changed to E V tau by ml. Expression for this is the expression drift velocity of free electrons. Similarly, for holes it will be V for holes as minus EV tau divided by ml. Here E stands for charge of holes. These two are the mathematical expressions for drift velocity of electrons as well as drift velocity for holes. We derive that expression by taking a semiconductor in initial state, the average velocities are 0, then applying external electric field, so drifting occurs and that velocity changes, and the average of that velocity is nothing but drift velocity, and mathematically we show the expression for drift velocity of electron as well as drift velocity for holes. Next, we can point out what is conductivity and mobility in case of semiconductors. So, the current density due to drift velocity of free electrons, current density due to drift velocity of free electrons J of E, that is minus N E V V, drift velocity of electrons, minus of E, charge of free electrons, here N, the free electron density, N free electron density. Similarly, current density due to drift velocity of holes, J of H is equal to P E V of H, V of H drift velocity of holes, E charge of holes, here is the P, the term P that stands for hole density. Hole density. Let we take this as equation number 1, that as equation number 2. So total current density, therefore total current density J is equal to J of H plus minus of J of E. We take negative sign as JE is opposite directed towards to J of H, drift velocity of electrons, and the current density due to the drift velocity of free electrons is just opposite to the current density due to drift velocity of holes. Therefore, we use the negative sign. J is equal to JH as P E V H plus N minus minus plus N E V E, or J is equal to, taking E as common, that is N V E plus P V H. Equation number 3. Let we define the conductivity of semiconductor. The conductivity of semiconductor sigma is the current density to that of electric field, applied external electric field. As a result, so sigma is equal to conductivity, electrical conductivity. In place of J, we write it as E N V E plus P of V H divided by E. Separating these two terms, so sigma is equal to E N V E divided by E plus P V H divided by E, velocity to external electric field, that is a term which we call as mobility. Therefore, electrical conductivity sigma is equal to E N in place of V E by E, that is mu E, plus P in terms V S by E that is mu h. Here we define V by E is equal to mu, that is the mobility. Similarly, V E by E, that is mu of E, mobility due to free electrons, which is named as free electron mobility. And V h by E, that is mu h, which is hole mobility. So finally, we expressed as electrical conductivity in terms of mobility and the relation between electrical conductivity and mobility. So here, with the help of this video lecture, we understand the concept of drift velocity, conductivity and mobility. First we derive the expression for drift velocity, and then conductivity and mobility in case of semiconductors. So with this useful and informative notes, let me wind up this session. Thank you.